Okay, so quantum mechanics. I just wanted to do this video to teach you guys about the basic ideas of quantum mechanics. And then after this, hopefully, I can make a video about quantum biology. And you'll have a foundation of knowledge to help you understand quantum biology. So quantum mechanics is all about the behavior of individual particles. We live in a macro world, a world of millions of trillions of molecules interacting with each other, and we just see like the statistical result of all of these collisions and things going on around us. But actually, the way that particles behave by themselves is very different to how we experience the world. Quantum mechanics is the fundamental, the basis of the world that we live in, but it seems like a separate world because it's so weird. It seems magical. So there are four main behaviors of four main quantum behaviors that I'll outline to you. They're all amazing. You may have heard that quantum mechanics is really hard to understand, but I mean, I'm not no physicist, and I just read a book about quantum biology, and the basics of it are really weird, but you can understand them, or at least know them. So the first behavior is wave-particle duality. Particles aren't just matter as such. They can switch between particles and waves of energy. So yeah, matter and energy can interchange just like that. You can also have particles in superposition, which means that they exist, say an electron can exist in two opposite states simultaneously. So for example, with me in my macro world, I could say that this light switch is on right now, and now it's off. That was cool. Now, that is the macro world. It's either on or off. But in the quantum world, particles can be on and off at the same time. So electrons can be in a state of upspin and downspin at the same time. I don't really know what upspin means or downspin means. It's not quite as simple as an electron that spins up, an electron that spins down, but they're two different states of an electron, and they can exist in superposition, both upspin and downspin. So that's superposition. Particles can also take part in quantum tunneling. Tunneling is where particles behave. They break through an energy barrier that is theoretically impossible. So if we imagine a normal enthalpy diagram for a reaction, you might have seen energy of products, energy of reactants, energy of products, an activation enthalpy, and then you get down to your products. But there's this energy barrier, which is of course this, that most of the time reactions have to go over. But in a quantum coherent state, quantum coherence is where these quantum behaviors can actually take place. That particle can just go straight through the energy barrier. It doesn't need the activation enthalpy. And that will be something very interesting in quantum biology that I'll talk about soon. So that's quantum tunneling. There's also entanglement. So in an atomic orbital, you'll have two electrons, and they exist in opposite electron spins. And like we said before, at the same time as existing in opposite electron spins, they are in both upspin and downspin at the same time. They are entangled because if you measure their electron spin, now measurement is just where you involve lots of interactions with trillions of particles or trillions of other things. Each of them have quantum behavior by themselves, but altogether it becomes decoherent. So that quantum coherence is destroyed. So if you measure the electron spin of quantum entangled electrons, one of them will instantly be shown as only upspin. It will now not have downspin. The other one will instantly be in downspin. And if you separated these electrons, and they've shown this in experiments to be true, once you measure this electron, it goes into downspin at exactly the same time as the other electron collapses its superposition, collapses its entanglement, well, collapses its superposition, in fact, going from both upspin and downspin into just downspin. And that process is instantaneous. They could be on other ends of the universe and it would still happen instantly, which means that whatever is connecting these two electrons is traveling faster than the speed of light. And that's what Einstein really struggled to get his head around, and he was skeptical of quantum mechanics because of this. So there you have it. That is quantum mechanics, or at least the basic principles of quantum behavior. So it's not that complicated, is it, really? It's just weird. Like, how can energy become matter? What is energy really? How can something be both on and off at exactly the same time? It doesn't make sense to us. And there's another very weird experiment that I don't quite understand a lot of it yet, but I thought I'd just tell you about it because it's really interesting. So it's called the Two-Slit Experiment. Now, in this experiment, you have a back screen, and you have a front screen. And the front screen has, as you can see, two slits in between through it, where, if I've got a gun, imagine a gun of just bullets or something, and I fire the gun, bang, 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 and it's going to go through, the bullets go through these slits, and are going to form a pattern on my back screen, like this. That's one slit that the bullets are going through, and then another slit that the bullets are going through. That makes sense in our world. That's what happens. Bullets or particles, matter goes through the slits, and it will make these marks on the back screen. Now, just with light or waves, energy and waves are very quantum things, so they often act differently to how we'd expect them to. Say I've got a source of waves, like psh, psh, giving out waves here. They're going through these two slits. If I cover up one of these slits, then we'll get a normal, exactly what we'd expect, a pattern like this through that one slit, because the light's going through one slit and hitting there. If two slits are open though, you get something really weird called an interference pattern, which I can't really draw in here that well, but it looks a bit like this. And it's where it will be very black, where lots of energy has hit it, and white, where it seems like there's been no light there. But how did black get up here? How did the light hit here when it was just going through here? Surely the light was travelling in a straight line. And surely, if it was going through these slits in a straight line, it would hit here. But it doesn't. It forms this interference pattern because light diffracts when it goes through these slits here. And when it diffracts, different waves cancel each other out and others complement each other. So where it's white, the waves have cancelled each other out. Where it's darker, the waves have complemented each other. So that's weird enough on its own. Now, this is the more interesting part. Here I've got an atom gun, and it's going to fire particles, or yeah, it's going to fire atoms. And when it makes this sound, it's firing an atom. So here's my two slits. Bang, bang. As it's doing that, again, it's forming this weird pattern here, this interference pattern. Now that doesn't make sense. We would have thought atoms would behave like bullets, like particles, but it turns out they don't in this case. We know that they start off as a particle, but as they're travelling through the slits, they act as a wave, and then once they get to the board at the back, the board takes a quantum measurement of them, causes decoherence, so they become particles again. So for some reason, they're waves between the atom gun and the board. If you just do one slit, close one slit here, the atom acts as a particle. Very weirdly, it just forms your normal particle pattern. Two slits acts as a wave. If we put a detector behind these slits, it would start acting as a particle again. Exact same experiment, but all we've got now is just a slit here, a detector here, and a detector here, and we are back to our previous two-slit pattern. But this still applies even if I only put one detector here and no detector here. So there's only one detector. Surely it's not going to affect the light that goes through here, but it turns out this detector that is measuring the wave not only collapses the wave into a particle down here, but the measurement also collapses the wave into a particle up here. And this here, I wouldn't be able to answer all the questions that I'm sure you would have watching this video, because I don't fully understand it. But I'm sure it will spark some interesting questions. And yeah, hopefully you can have a good think about that and get ready for the quantum biology video that I'm making soon. So have a good week.